Right. Okay, yeah. Good morning, lads and ladies. Welcome back to Calc 2. Last time we introduced these new things called power series. And today what we're going to do is we're going to start exploring how to find a power series representation for a function that's given to you in some other way. Specifically, if I give you a function the way you're used to getting it, right, like an algebra formula for f of x, can you take that algebra formula and somehow manipulate it until you arrive at a power series? Obviously, the answer to the question there is yes, but the details can be a little bit, sorry, my cat's flew collars. But the details can be a little bit hazardous. So what we're going to do today is get some practice using some known facts, specifically the geometric series formula that we cooked up in section 11.2, together with the calculus operations of integration and derivatives to find power series for a bunch of other functions. The power series that we're going to find are going to serve as starting points for problems in the future. So what we're doing today is sort of a combination of two things. I'm going to be teaching you a new skill, how to come up with power series for a function. And then I'm also going to give you a few power series that we cook up in this way that you need to remember forever and ever, amen, because we'll be using them as starting points in future problems. Let's go ahead and do the thing. And as cute as you are, Nala Kitty, you're going to have to move, big girl. Hey. Get it, girl. I know, but you can't do the calculus. You don't know the calculus, so you gotta move, okay? Okay. All right, so. Let's get to it. This is MAC2312 section 004, which is Calc 2. And the date today is it the 23rd or 24th? 23rd of March, 2022. What we're going to do today is discuss how to represent functions as power series, which is section 11.9. So last time we did 11.8, which was just like an introduction to power series, finding intervals of convergence, radii of convergence. The other kind of big thing that's not mentioned here in the subject line is that this is the section where we learn how to integrate and differentiate power series. And that's a big result. The main tool for this section is what I'm going to refer to as the geometric series trick. And that is that if you have the series sigma n from 0 to infinity of, I'll write it in terms of the variable u, sigma n from 0 to infinity, u to the n, this guy is equal to 1 divided by 1 minus u, right? That's a geometric series. And as long as it converges, as long as the absolute value of u is less than 1, then this guy will have sum, which is the starting term. And since we're starting here at n equals 0, the first term of the series is 1. Starting term divided by 1 minus the common ratio. And this is valid for any u which has an absolute value less than 1. That's kind of it, right? That together with integration and differentiation is kind of it. And I'll show you how to integrate and differentiate series. But before I do that, I just want to give you a few examples. So I can tell you to find a power series for the function f of x equals 1 over 1 plus x. We're going to use the geometric series trick. I'm going to use the fact that 1 over 1 minus something is sigma that something to the n, sum from 0 to infinity. So f of x here is 1 over 1 plus x. And that's almost in this form. What I need to do is write this in this form. Then I can apply this result from 11.2. Well, 1 over 1 plus x, we just do some algebra, right? We get sneaky with our algebra. I can write 1 plus x as 1 minus negative x. And now this is in this form. Here's u. So I can plug into this formula with u equal to negative x, and then boom, all of a sudden I've got a power series. Series would be sigma n from 0 to infinity, u to the n, but u is negative x. So this is negative x to the n. Now that doesn't look like a power series yet, right? This isn't in that form that we gave in the definition of a power series. So we always want to simplify these things to write them in that standard form, like Cn times x minus a to the n. The only thing to do here, remember that negative x is negative 1 times x. So negative x to the n is negative 1 to the n times x to the n. And now this does look like a power series, right? This looks very similar to all the power series we were playing with on Monday. Job done. The only other thing you need to do here is figure out your interval of convergence. So this function really can be written as this power series, but that's only valid if the series converges. So we have to find the values of x for which the series converges. And we know that that can be a real pain in the ass. We know that one way to do that is to run the ratio test on this thing and then check your endpoints and run 2 different convergence tests, one for each endpoint. Thankfully here, we know that this step is kosher. If and only if the absolute value of your common ratio is less than 1. It's a geometric series. So that would mean I need the absolute value of negative x to be less than 1, because u is negative x. The absolute value of negative x, though, that's just the absolute value of x, right? That's what absolute values do. They gobble up negatives. And then you can expand this using the unpacking rule that we learned on Monday. And you can test the endpoints if you want to, but you don't have to, not here. Because remember, this is the whole story. There is no question of whether or not this series converges or diverges when u is equal to 1. When u is equal to 1, that's a divergent geometric series. You need the absolute value of u to be strictly less than 1. So if you're just using the geometric series trick, if you don't do anything else, then your interval of convergence will always be open. So the IOC for the series is the open interval from -1 to 1. And that's it. That's your answer. This is a nice gentle starter problem. Is there anything here that we want to look at a little more closely? Any questions about the algebra steps? So in passing from here to here, what I'm doing is really just simplifying this piece up top into this piece right here. Let's see, I can partition off a bit of space over here to see what's going on. So negative x to the n, that's the same as -1 times x all to the n. And then our rules for exponents say that, okay, if you have two things multiplied all raised to the n, then I can give that power to each of them individually. The other question there is, when will we encounter brackets in our interval of convergence? The short answer is if you integrate a geometric series. That's the short answer. So if in 11.9, in this section of the book, our starting point for coming up with power series is always going to be this geometric series trick. And if this is the only thing we employ, then the interval of convergence will always be open, because geometric series always diverge at their endpoints. Right? At 1 or -1, this is always going to be a divergent series. And no matter what you do with your inequality here, it's always coming from this guy. And those endpoints will always be the numbers that make this thing equal to 1 rather than less than 1. So if all you do is employ the geometric series trick, then you don't need to worry about brackets or parentheses. It will always be parentheses. One of the other things we're going to see in this section is that you can do the geometric series trick and then take an integral, or do the geometric series trick and then take a derivative. And in those cases, you need to be a little bit careful about whether you have brackets or parentheses. I'll give you some rules. I'll give you some guidelines you can follow. And if you're ever in doubt, you can always test the endpoints. It will never hurt you to test them. It just takes up extra time. These are good questions. Any other questions? Okay, let's try something else. So let's find a power series for f of x equals x over 1 plus x squared. Roughly the same vibe as the last one. We need to bash this with the algebra hammer until it's in the form where I can use my geometric series trick. Focus. First thing I would do is recognize that having that x upstairs is the same as having an x out front and a 1 upstairs. And I want a 1 upstairs because my geometric series trick is 1 over 1 minus u. So I've got a 1 up here. I've got a 1 here. This is a plus. So just like in the last problem, I'm going to write that 1 plus downstairs as 1 minus the negative of, in this case, x squared. And be mindful, the square here is inside the parentheses, not outside. I don't want to square the negative. I just want to square the x because it's just the x squared here, and I need this to be the same as 1 plus x squared. But adding something the same as subtracting the negative. So there's u. I can plug into my geometric series. So there's a little more simplification to do here. Rather than just negative x to the n, I've got negative x squared being raised to the n. I also have this x out front. I want to write this as a series, just sigma cn times some powers of x or x minus a, whatever, something that fits that standard definition of a power series. So first we need to clean this up. Then I can bring the x inside. Negative of x squared to the n is negative 1 to the n, just like before. And then x squared to the n is x to the 2n. The algebra there is the same sort of thing. Just with one extra step. So this is like negative 1 times x squared to the n. It's negative 1 to the n times x squared to the n. Hard time focusing today. And then x squared to the n, that is x to the 2n. And my last step here is to bring this x inside. So sigma n from 0 to infinity, negative 1 to the n, x times x to the 2n. So that's this guy coming in. He doesn't have any n's in him, so he can pop in and out of the series at will. Last thing, x times x to the 2n is x to the 2n plus 1. So this is sigma n from 0 to infinity, negative 1 to the n times x to the 2n plus 1. And to find your IOC, you could take this and run it through the ratio test, solve the inequality, and check the endpoints. That's an option. You can always do that. But if you want to do it quickly, you come back here. We know this will converge if the absolute value of u is less than 1. Which means the absolute value of negative x squared is less than 1. It's basically the same steps. The negative goes away because of the absolute values. The square can pop out of the absolute values. You can take square roots and then unpack. So the IOC is again the open interval from negative 1 to 1. And because I didn't do anything besides use my geometric series trick, it was just algebra and geometric series, I know that the IOC will be open no matter what. Your final answer. I'm going to do one more of these, and then we're going to introduce this idea of integrating and differentiating series. So questions on this guy? Okay, one more. So let's find a power series for 3 over 7 minus x cubed. It's more of the same. It's more of the same, just bashing it with the algebra hammer until I can use my geometric series formula. So I can pop the 3 off the top. The challenge here is that I don't have a 1 down here in this position. I have a 7. So I need to turn this into a 1. And the easiest way we can do that is by force factoring out a 7. So there is no common factor of 7. There's a 7 here. I want this to be a 1. So if I factor out or divide through all the terms in the bottom by 7, then I'll have 3 times 1 over 7 times parentheses 1 minus x cubed over 7, like this. So of all the algebra tricks we use, this is maybe the fanciest. It's nothing crazy, right? We're just factoring a 7. I've got a 3 upstairs here. I've got a 7 down here. I'll write that as 3/7 times 1 over 1 minus x cubed over 7, like this. And the idea is that this piece now fits my geometric series formula. Here's u. This will be 3/7 times the sum from 0 to infinity, x cubed over 7 to the n. A little more simplification to do here. This is going to be x to the 3n over 7 to the n. I can bring that 3/7 inside the series. And then I can write x to the 3n times, or divided by 7 to the n as 1 over 7 to the n times x to the 3n. And then I can multiply these two fractions. 3 times 1 is 3. 7 times 7 to the n is 7 to the n plus 1. So you get sigma n from 0 to infinity, 3 over 7 to the n plus 1 times x to the 3n. So this is your power series. The IOC work Basically the same stuff that we were doing before. We need to solve the inequality. Absolute value of u is strictly less than 1. Here u was x cubed over 7. So this is the absolute value of x cubed over 7 is strictly less than 1. I can give the absolute values to the top and bottom separately. The absolute value of 7 is 7. I can multiply both sides by 7. And I can pop the power out of the absolute values. Then taking cube roots. Gives me this. And finally, I'm ready to unpack the inequality. That's negative cube root of 7 is less than x is less than the positive cube root of 7. So the IOC, the open interval from the negative cube root of 7 to the positive cube root of 7. Excuse me. And it's the same thing you would get if you ran the ratio test and checked endpoints. It's just much, much faster. Questions on this guy? Remember from geometric series converge if and only if the absolute value of the common ratio is strictly less than 1. So this is the condition that guarantees that the series converges. All right, if you look at this step, just this series, this is a geometric series. The common ratio, the thing being raised to the n, is x cubed over 7. So I need the absolute value of that thing, which is this, to be strictly less than 1, which is where this comes from. So remember the using here is that sigma n from 0 or wherever of u to the n converges if the absolute value of u is less than 1 and diverges if the absolute value of u is greater than or equal to 1. That was the theorem we had in 11.2. The other comment there is that coming up with this series seems kind of easy. Where's the crazy part, right? If it's just this algebra and plugging into the geometric series formula, why do people get scared of power series? There's two reasons people get scared of power series. One, they're not good at algebra. That's an obvious, like, you're fucked. You got to practice the algebra. The other thing, and this is the main thing, is that remember the rest of 11.9 is about integrating and differentiating series. So that's where it gets a little interesting. So that's what we're going to do now. That's what we're going to spend the rest of the class on, is talking about how to take derivatives and antiderivatives of infinite series, power series, specifically power series. So this series represents a function, right? This is like a big, long polynomial. And that big, long polynomial is one way of writing this function. What if I want to differentiate this function, take the derivative of it? Well, there should be some way to take the derivative of this thing that matches up with that. But what if I want to integrate this function? Well, I mean, we know how to integrate functions. We spent the first quarter of the semester doing that. There should be some way to integrate this thing that matches up with that. These are two big results, and I'm going to give you the theorem. I'll do my best to justify the theorem to you, and then I'll show you why it's so damn useful. The other thing that scares people about power series is what's coming in the next section, 11.10, which is where we get Taylor's theorem, which is a very general way to get power series for functions, but the formula just looks a little scary. So we'll build our way up there. So let's say assume that f of x can be written as a power series like sigma n from 0 to infinity Cn times x minus a to the n with radius of convergence r. Then two things are true. The integral of f of x dx, which would be the integral of this series, can be computed nicely. I'm doing an indefinite integral, so we're going to have a plus c, and we like to write that plus c out front. And then the trick is to like cover up all of this stuff. Oh, sorry, I need a dx here. The trick is to cover up all of this stuff and pretend like you're just integrating the x minus a to the n term. This would be a little micro u sub, right? Like u equals x minus a, and then you'd be integrating u to the n. By the power rule, that should be u to the n plus 1 divided by n plus 1. And that's precisely what you get. You get sigma n from 0 to infinity Cn times, I'll write it as 1 over n plus 1 x minus a to the n plus 1. Again, the way to see this, just cover this stuff up. You're really just integrating this little power rule thing. So you add 1 to the power and then divide by the new power, just like integrating x squared, right? You get x cubed over 3. Integrating x to the n, you get x to the n plus 1 over n plus 1. The only thing is here it's x minus a, so it's a little micro u sub. U equals x minus a, du equals dx. This becomes u to the n, which integrates to u to the n plus 1 over n plus 1. Boom. We write the plus c out front because we don't want it to look like the c is inside the series. The c is outside the series. And so that's how you integrate a power series. What about differentiating a power series, f primed? Well, this would be the derivative ddx of the original series, sigma n from 0 to infinity, Cn times x minus a to the n. This goes almost exactly how you would think. Again, cover up the series and the Cn's, and what you see is you're differentiating x minus a to the n. Well, that's a little baby chain rule thing, right? That would be n times x minus a to the n minus 1 times the derivative of x minus a, which is just 1. And that's what you get, n times x minus a to the n minus 1. You notice I left something off, though. I didn't tell you where this new series starts. The original series starts at 0. This new series might start at 0, might start at 1. In fact, as I've written it here, this new series would have to start at 1. And I'm going to explain why. But first, let me just go ahead and finish writing the theorem. First, just write this down. Trust me for a moment, and I'll justify this claim. I know it's a little weird. The remainder of the theorem is that where both resulting series also have radius of convergence equal to r. So when you integrate or differentiate a series, you don't change the radius of convergence. The ROC was 1 when you started. You take an integral. The ROC will be 1 when you finish. If the ROC was 5 when you started, take a derivative. The ROC will be 5 when you finish. I'm not going to prove this to you. The proof is very straightforward. If you're just thinking about the symbols, you just integrate one term at a time or differentiate one term at a time. But I do want to address this issue of bumping the starting index. So y sigma n equals 0 to infinity become sigma n equals 1 to infinity for f primed. And the answer is because the n equals 0 term in the original series was constant. And the derivative of a constant is 0. So what does that look like? That's when I take the derivative here, I'm just going to write this out long form. This basically amounts to a proof of the theorem, but whatever. This is the n equals 0 term. This is the n equals 1 term. This is the n equals 2 term. This is the n equals 3 term, and so on. What's going to happen when I take d dx of this? I differentiate one term at a time. D dx of the constant c0, that's 0. Plus d dx of c1 times x minus a. Well, the derivative of x minus a is just 1, so that's going to become c1. Plus d dx of c2 times x minus a squared is c2 times 2 times x minus a to the 1. Power rule, right? Just power rule. Plus the derivative d dx of c3 times x minus a cubed is c3 times 3x minus a squared in power rule. So the n equals 0 term vanishes. Because d dx of a constant is 0. So the original series had an n equals 0 term. It was constant, had an n equals 1 term, had an n equals 2 term, had an n equals 3 term. But the resulting series doesn't have an n equals 0 term. He's gone. So this resulting series is just C1 plus C2 times 2x minus a plus C3 times 3x minus a squared plus and so on. And if you had to write this in sigma notation, you'd go, oh, well, that's sigma n from 1 to infinity, Cn times n times x minus a to the n minus 1. Here's where it gets a little sticky. Not all power series start with a constant term. Some power series start with an x term. Some start with an x squared term. So the rule is we bump the starting index up by one when differentiating power series if and only if the starting term is constant. I'll show you an example or two. Now, if you're wondering what parts of this do I need in my notes, what parts of this do I need to remember for the test, let me show you. This. Of course, the theorem itself, hugely important. If and only if the starting term is constant, that's what that said. So what do we need in our notes? This theorem that tells you how to integrate and differentiate power series. The blue is optional, right? I think the blue will help you understand the second formula. The red is necessary. So the black and the red. Yeah, so if and only if the starting term is constant. Oh, or here, this word is bump. So, example time. Let f of x be 1 over 1 minus x squared, and find a power series for f primed of x. What I'm going to do is find a power series for this thing and then differentiate it. So by the geometric series trick, f of x, which is 1 over 1 minus x squared, is sigma n from 0 to infinity, x squared to the n, which can be simplified as sigma n from 0 to infinity, x to the 2n. And the series looks like 1 plus x squared plus x to the 4 plus x to the 6, and so on. That's the power series for this original function f. Now, what I've been asked to do is to find a power series for its derivative. So f primed here is going to be ddx of sigma n from 0 to infinity x to the 2n. And remember what the idea here is, you just ignore the sigma, basically. Just differentiate the x to the 2n. So you get 2n times x to the 2n minus 1. And the new sum is going to run from n equals 1 to infinity. We changed the n equals 0 to an n equals 1 because the series we're differentiating does have a constant term. So because the original series did have a starting term which was constant, when we take the derivative, we are going to bump that index up. And the mechanics of taking the derivative couldn't be easier. Again, just pretend like the sigma isn't there. You just differentiate x to the 2n, and you get 2n x to the 2n minus 1. Not bad, right? That's it, we're done. Okay, another common thing to do is to calculate an integral as a power series. And it's the same sort of idea. You write the function as a series, and then you integrate the series. Of course, you know how to integrate this normally. I'm just using this as a very simple example. We begin by saying here that f of x is 1 over 1 plus x, which is 1 over 1 minus negative x. So using my geometric series trick, this is sigma 0 n equals 0 to infinity, x to the n, which is sigma n equals 0 to infinity, negative 1 to the n, x to the n. So the integral of f of x is the integral of this series x. And again, you just ignore all of this stuff, right? Just integrate x to the n dx, we write our plus c out front, sigma n from 0 to infinity. You never have to change the index when you're integrating, only when you're differentiating, and even then only if the original has a constant term. So here we just take the regular antiderivative, x to the n. When you integrate that, the power goes up by 1. So this will become x to the n plus 1. And we divide by that new power. You're done. Questions on these two examples here? Okay, then I'd like you to think with me for a moment. I said a second ago, you know how to integrate this. You don't need power series to integrate 1 over 1 plus x. What is the antiderivative of 1 over 1 plus x? So this is not a part of that example problem anymore, but I'm going to use something that we just did in that example. We know that the integral of 1 over 1 plus x dx is the natural log of 1 plus x. Right? You do a little u sub here, u sub u equals 1 plus x. This becomes 1 over u to u. You get natural log of x plus a constant. I'm going to leave the constant off here because there's going to be a constant here. So by the previous example, the natural log of 1 plus x, which is the integral of 1 over 1 plus x dx, must be equal to c plus sigma n from 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1, for some choice of the constant c. What I'm going to do here for you is solve for c, and then you will get from this a power series for the natural log function. I want the series centered at 0, so instead of natural log of x, which is not nice at 0, right? It's undefined at 0. I'm going to do natural log of 1 plus x. So writing out the series, we get that the natural log of 1 plus x is c plus. When I plug in n equals 0, I get negative 1 to the 0 over 1 times x to the 1. When I plug in n equals 1, I get negative 1/2 x squared. When I plug in n equals 2, I get plus 1/3 x cubed, and minus 1/4 x to the 4, and so on. So plugging, I'm going to plug in the center 0 for x. I know that the series should converge. Power series always converge when you plug in their center, right? The center is always inside the IOC. We get on the left-hand side the natural log of 1. On the right-hand side, c plus 0 minus 1/2 times 0 squared plus 1/3 times 0 cubed. That's 1/4 times 0 to the 4, and so on. Every term here is 0. Natural log of 1 is 0, so I get 0 equals c plus 0, which means the choice of c, which is correct, is 0, if I want this to be equal to the natural log of 1 plus x. Therefore, this is the second of 3 very important series formula that I'm going to give you today. I'll give you the third one in just a moment. The natural log of 1 plus x is straight up equal to sigma n from 0 to infinity, -1 to the n divided by n plus 1 times x to the n plus 1. And the IOC here it's not entirely obvious. We started with a geometric series, but then I took an integral. And when you integrate or differentiate a power series, the radius of convergence cannot change, but the endpoints can change. You can go from a bracket to a parentheses, or a parentheses to a bracket. So the geometric series that I started with for this guy had the open IOC from -1 to 1. And when I integrated it to get this series, something neat happens. We picked up the endpoint at 1. So this new series has this as its interval of convergence. And this is the second super duper important power series from today that you need to remember forever and ever. First one being the geometric series thing. That's pretty good. One second. Okay, so the geometric series, this, 2 very important power series for me. There's one more that I need to cook up for you, and it goes almost the exact same as this for the inverse tangent function. We begin with this, right? We know that 1 over 1 plus x squared can be written as a power series sigma n from 0 to infinity, -1 to the n, x to the 2n. We did that earlier. This for all x in the open interval -1 to 1. So if I integrate on both sides, then the left-hand side is going to become the inverse tangent function. The right-hand side will be a power series for the inverse tangent function. Now there's a plus c over here and a plus c over here. Just like on the last one, I'm going to group those into one constant, which I'll put on the right. When I integrate this guy, I'll get this. I'm evaluating this. At x equals 0. Inverse tangent of 0 on the left equals c plus, I'll write it out here, this would be 1 x, this would be 0 minus 1/3 cubed, fifth, the inverse tangent of 0 is 0. So again, what we're going to get here is the constant c is 0. So the inverse tangent of x, sigma n from 0 to infinity, -1 to the n, 2n plus 1 times x to the 2n plus 1. The interval of convergence for the series I started with, the IOC for the original geometric series, was the open interval -1 to 1. When I integrate this series to turn it into this series, something cool happens. Imagine you plug in 1 for x, so this all goes away. The resulting series here is convergent. It's conditionally convergent, but it's convergent. And if you plug in -1, the same thing happens. So the IOC for this guy is closed. And that is your last super serious series formula for today. Now those three series, they're going to be very important starting points for us moving forward. In fact, some of the problems in your homework ask you to find a series for arctan of x cubed, or to integrate arctan x over x, or something like that. All of those problems, you begin with this guy. Maybe you plug something in for x cubed or something, and then do your integral. On Friday, I'm going to pick it up here. We're going to see how we can use these series to solve problems that previously we could not solve. And I'll also show you how to cook up some more series through differentiation, because I know that that's generally a little bit challenging. But I would like you, between now and Friday, to solve as many of those homework problems as you can. If you spend some time getting stuck or banging your head against the wall on one of them, that's okay. We want you to have that experience. That sort of struggle is where deep understanding comes from. So make sure you have these three series, the inverse tangent guy here, the natural log guy here, and the geometric series here, all stashed somewhere safe in your notes that you can get to them in case of emergency, because whew, you don't want to have to cook these up every time you need them. You will need them a lot. It will often be the point from which we begin. It should not be something that you have to do a bunch of work to get and then go somewhere to begin with these kind of series problems. Like I said, next time we're going to see how to solve lots of integrals and stuff that we couldn't solve before by writing the integrand as a power series and then integrating it. It goes very much the same way we did the examples today. Solve as many of the problems in the homework as you can by Friday. On Friday, I will show you how to solve the last few more challenging ones there. And then we're going to be ready for Taylor series. Taylor series, special case power series, or a special way of looking at power series, which connects the series itself to the derivatives of the function. And that's really where the kind of challenging concept stuff comes from. So make sure you're good at this. And then next week, when we drop Taylor series, they won't be so scary for you. If you have any questions, you can come see me in office hours, or you can send me a Canvas message on email, any of that normal stuff. Otherwise, I will see you guys on Friday. Yeah, if you requested the test be graded early, I'm going to get them knocked out today. I'm working on that already. I only got, I think, 2 or 3 requests, so I think I should be able to get them all done for you before 5 p.m. today. That's the goal. Alrighty, then that's it for me for today, guys. I will see you next time. Take good care, work hard on that homework, and we'll do more on Friday.